In the previous session, we were looking at a topic called as flat top sampling. And in the flat top sampling, first we looked at how the representation happens. We looked at the signals representation in time domain by using a signal and its sampled version. And the samples will have flat tops. It's not going to sample the complete signal as it is. It's going to sample at a given point, and it is going to retain that value throughout. And then we try to give a representation for each of the rectangular function in terms of the standard rect function. Then we understood that by performing what is called as a convolution, we can get the required answer. Then we applied the same concept of convolution, and at the end we could get an equation for the S of f, and that S of f has the G of f as it is, right? So which means I can come back to the time domain. And then we introduced another term called as the aperture effect, right? That is because of the sinc function present in the equation. Okay, so till there we had discussed, right? And the next topic that we are going to see today is the PAM. PAM stands for pulse amplitude modulation. Okay, now this is the explanation corresponding to the concept we discussed already, right? I'll just show you the diagram. This itself is actually called as a PAM, right? When the whole signal is represented in terms of the pulses. Okay, so we have a signal G of t, and it is described by periodic sampled values, right? That's what is S of t. If we try to represent a G of t in terms of this S of t, right, we can transmit the signal using the analog pulse modulation, wherein the sample values modulate the amplitude of a rectangular pulse train. So we can see that there is a rectangular pulses over here, and those pulses, they are being modulated by the sampled values. Okay, so that itself is what is so this particular technique we just simply called the we discussed only about the samples. We call the samples as a flat top samples. If you use a flat top sampling technique and you do the modulation and you try to transmit the message signal, right, then the modulation technique is called as the PAM technique, or the pulse amplitude modulation technique. So let's quickly write that one point which I just try to define. Okay, so that is, if a message signal, that is the G of t, is described by periodic sample values. So when I try to represent in that way, this means it can be transmitted using analog modulation. So in this particular case, I can write wherein the sample values modulate the amplitudes of a pulse train. Okay, so here we need one diagram just to explain that what we are doing. So I'll just copy this already existing diagram. So the fundamental idea is that in this particular scenario, I have a analog signal, I sample it out, and the sampled values are used to perform the amplitude modulation of the rectangular pulses, right? So we have the rectangular pulses of a fixed amplitude, say 1. So whenever the sampling happens, the sampled values will be used to fix the amplitude of our uh, rectangular pulses. You see that I have sampled it here and I fix that value throughout. Sample it, fix it. So sample the value, fix the value. So that's what it's happening there, right? So I sample and I fix that amplitude throughout. Sample and fix it. So right. So that's why the above sentence says that, right, we are trying to perform the modulation wherein the sample values, whatever you sampled, that will modulate the amplitude of the pulse train. Okay, so that's what is the meaning. And so this is a diagram showing that. Now in this diagram, right, we can see that uh, what type of sampling technique we have used. It's a flat top samples. So the amplitude of each pulse it corresponds to the value of the message signal g of t at which at one of the edge, preferably it is a leading edge of the pulse. So leading edge means the where the signal amplitude goes too high, right? So that side. So this particular side edge is called as a leading edge. So every pulse has a pulse amplitude will be decided by the leading edge of that pulse. Okay, right? So that's very clear now. So let's try to write a sentence about the same. So the above, okay, I can show the graph shows PAM signal implementing the flat top flat top sampling technique. Right, in this particular technique we observe that amplitude of each of the pulse corresponds to the value of the message signal at the leading edge. That's very important, so we'll write that the amplitude of each pulse corresponds to the value of the message signal, which is a message signal, we denoted that as g of t, right, at the leading edge, at the leading edge of that particular pulse. Okay, now, so this type of modulation, right, is, we can see that there is a sampling operation with the sampled values corresponding to the initial sample value that is present at the leading edge of the pulse. So the fundamentally we understand that the flat top sampling concept which we had discussed earlier, right, is the basis for the PAM technique. Okay, so the result already we have seen, right? We can see the graph over here implementing the final results of the PAM modulation technique. Now, whenever we are trying to represent a function using a rectangular pulse, you see that the rectangular pulse has a fixed amount of the DC content, right? You are trying to add a DC content. So AC component is the varying component, but you see every pulse has a DC component because its amplitude is fixed. For a certain given duration, the amplitude of the pulse is fixed. So that means you are trying to add the DC component to your modulation technique. Okay, so that's one very important concept related to this technique. The PAM technique adds certain amount of DC component to the waveform. This is because it's not just for this, just this technique. It is true for every technique that you use fixed amount of pulse waveforms in your final signal. Okay, but there is a major application of this technique, that is you try to send this signal, you try to do a modulation plus multiplexing, specifically that's called as a time division multiplexing. The PAM is widely used over there, though it has, right, there is another concept called as a bandwidth requirement, right? So what happens here is that the bandwidth required to preserve this pulse shape, normally that is more than the message signal bandwidth. The message signal will have certain amount of bandwidth. Okay, for example, you see I have a message just like this, right? So that has, what is the bandwidth of this? Let us say it is fixed, correct? It's just fixed like plus w and minus w. So I have g of t here, this is g of f. You see it is fixed bandwidth, right? F versus this. But whenever you try to perform like this, what is the bandwidth requirement? Can you make a guess? So I'll write f here saying that I'm taking the Fourier representation. What is the bandwidth requirement? What shape you get here on this side? I'll write S of f. Either you can guess the shape or you can even tell me the answer. What is the bandwidth required? Anything is fine. Both are related to each other. Any answer you tell is okay for me. See, on the left side, I have a rectangular pulse. What is the Fourier representation of a rectangular pulse? Actually, not one rectangular pulse, many rectangular pulses. Correct? Okay. So when we have one of the pulse you consider, that's enough, right? What take one rectangular pulse and take its Fourier representation. What do you get? It's a sinc function. Perfect. So sinc has infinite bandwidth, correct? So it actually, right? It starts from here, it goes like this, and it goes all the way till infinity, correct? Again, I'm writing only one pulse, sorry, the Fourier representation of one pulse. You have multiple pulses. So pulse getting shifted means you even multiply by a exponential signal. So it actually becomes more wider. So all the way from minus infinity to plus infinity. So that means when I converted my message signal, which is the analog signal that you see here, into the PAM signal, right, the bandwidth requirement is actually, right, exceeds whatever you had allocated only, it's a baseband signal, so just w hertz, right? We have only w hertz available for us for a transmission, but because of the conversion of the signals into the PAM representation, we have a wider bandwidth requirement. So I'll write that as well. Okay, so the total bandwidth required to preserve the pulse shape, right, exceeds the bandwidth of the message signal. Okay, so the bandwidth means I'm actually referring to capital W. So originally the bandwidth which is allowed or allocated is simply W hertz. But as we can see, it is much greater than this, right? As shown in the above waveforms, right? So so we have, right, we have to balance, right? There is advantage and there will be disadvantage for this. So since you have a bandwidth requirements like this, there is no meaning in sending a single message. Okay, right? In the sense, I have only one message to send. There is no meaning in sending that over all the possible bandwidth from minus infinity to plus infinity. There is no meaning for that. Correct? Are you understanding what's the point? I have only one message to send, but you cannot use the whole bandwidth, right? So what you use, you have to use multiple channels. You have to bring the concept of multiple channels by using a concept called as multiplexing, right? So therefore, so I should write single channel communication system with PAM is not worth, right? Because whether you see if there is a system which actually requires infinite bandwidth, so with the infinite bandwidth we are supposed to send n number of messages simultaneously, not a single message, right? So that's why, right, we implement the multiplexing, right? So single channel communication system with PAM is not worth, so we go for multiplexed communication system is suggested for PAM. So whenever you want to go with the PAM, the practical implementation, right, uses multiplexed communication systems. So let's look at what do you mean by a multiplexed communication system with the example. So the one which is very famous is called as the time division. It's called as a time division multiplexing. Right here, you send n number of messages simultaneously, okay, over various time slots. Okay, we'll look at that concept now. So first, let's look at the diagram implementing this time division multiplexing systems. So this is in short denoted by TDM. Okay, all right. So let us say that we have multiple messages to be transmitted. Okay, so the first message, I'm going to call this is my message signal. So I'm going to call this is say G1 of T. So as soon as a signal comes into picture, right, I will pass this through a filter which performs which eliminates the concept of aliasing. I should not have an aliasing, right? So we call it as, okay, let me use a simple filter, then we'll give a name to that. Okay, so there is a LPF. It's a low pass filter, right? It is passed through this, then take up another signal, G2 of T. So there is another LPF. Let's take say 3 signals for our explanation purpose. So I need another signal and another low pass filter. So let's call this is G3 of T, the third message signal, and we'll pass it through another filter. Okay, so there is another LPF. All right. Now, there is a important part in the time division multiplexing system. That is, you see, simultaneously at a given point of time, I cannot send all the signals because each signal requires infinite bandwidth. Right. So what we do, we divide the time allowed for the communication. Let's say I have 10 seconds to send 3 message signals, right? Let's say I divide the 10 seconds into 1 second interval for the time. Let's assume, right? 1 second. So totally there are 10 seconds, right? Each second, I'll try to send a part of message signal 1. Next second, this. Next second, this. Then I come back. Then next, once again, this. Once again, this. And this. This is repeated. You see, first, then second, then third, and so on. This is repeated. Okay, until and unless you finish all the messages, right? Yeah, every message gets a time slot. Okay, so each time slot you send a portion of the message signal. Once all it goes one, then we send the second signal one part, then the third signal a part, then you go back to message signal one once again, then you send another the second half of that signal, and so on. This is repeated. Okay, this is the whole concept of time division multiplexing. But you see, right, I have to select signal one by one, right? So at a given point of time, I'm allowed to select only one signal. So how do I do that? I will use a specific part that is called as a commutator. So there is a requirement of a part called as commutator. Okay, so commutator is denoted by a structure like this. That's a standard uh, representation of a commutator. It connects to one of the uh, it connects to one of them at a given point of time. So I can try to. So this is how they are connected, but at a given point of time, the connection will be there with only one of them. Okay. Now, so let me show you how this works. So at the center, you have let me say I have something at the center. Now, so this is actually connected to one of them. I'll show you it's getting connected to one of them. Let's say like this. So you see, as of now, it is connected to the LPF, the LPF corresponding to the G2 of T, in the sense that this G2 of T is being transmitted. Okay, like that. So now I will connect this to the next part of the circuit. So there we are connecting to a modulator. So that is the pulse and PAM generator. In the sense, whichever message is coming, it will convert that into the PAM signal. Now it's fine for us. So second signal is being transmitted in the form of PAN using the complete infinite bandwidth. But this happens for a very short duration, not continuously. So it is okay. Okay, fine. Then once the signal is PAM signal is generated, we will make it to pass through the channel. Right? It is decided by the one who designs the system, right? They can choose whether you want to communicate using the two wire system, or you want to use an antenna, send it to the space, anything, or is it an optical fiber communication, anything, whatever. Okay, then we have the next part coming up. So here we do the demodulation. So it's the PAM demodulator. So whatever operation that was done in case of a PAM modulator, now it will be demodulated. Okay, right. Then see, in a sense, right now, so there are three messages sent. Obviously, all the three messages will never go to the same person. They will have to be delivered to three different locations. Correct? In the sense, first message should go to the location corresponding to the first message delivery, right? Destination of the, so we call three deliveries here. So three message sources are there, three destinations will be there. So there should be a synchronization mechanism which tells, right, where to deliver this. So again, what you need another commutator. So that's an indication that I need another commutator. Okay. Okay. Let's assume like this. Now, so since the message is coming from a source that is corresponding to the second message, I will even connect this to the second message delivery system. Okay, so this is how I'll show the connection. Okay, now I need three destinations. So before I deliver something to a destination, I'll write the low pass filters again, because there may be unwanted messages coming up. So this is a low pass filter number 2, and this is a low pass filter number 3. Okay, if it is connected to this, it will be delivered to this, the first LPF. Anything coming from the second will be delivered to this, and anything that comes from the third will try to get delivered to this. Okay, so corresponding to each, we have one output that is allowed. So it will be okay. I can write. I can call it as simply output. Okay, that is output. Output number 1. Okay, so that is output number 2, and this is output number 3. Okay, so this is the whole system of time division multiplexing. Okay, I'll try to show everything in a single thing, single screen. Okay. All right. So we can see that 3 messages have been considered. All will pass through this. Okay, I'll write the word commutator. So this part is a commutator. I have another commutator over here. That's it. Okay, now you see I need a synchronization system that decides at what time what message is being transmitted. In the sense, is it corresponding to first one or is it corresponding to second one, should be known. In the sense, when the second message is being transmitted here, you see it is connected to the second LPF, saying that okay, now the message is coming that is corresponding to the second one. Otherwise, you see what happens if at all it is connected to this, message delivery went wrong, that goes wrong. Correct. So what we'll write here, it's a synchronization. This is synchronization mechanism. Right? Both will be synchronized. Both the commutators are synchronized. Right? So the second commutator has a specific name called decommutator. In the sense, commutator will pick up from the second one, decommutator will deliver to the second. When it is picked from the first LPF, it will deliver to the first, and so on. So that's why the name is decommutator. Now, so PAM signal needs an input, right? I'll write it here. So what's the input required for PAM? That is a timing pulse. Timing pulses. So you see the similar timing pulses are even required for the demodulation as well. So we'll once again write the timing pulses. Okay, now, so let's quickly write the explanation for this. So in this block diagram, whatever has been represented, I'll try to write about that quickly so that when you read, you will understand. Okay, right. So first we take up the several input message signals. In this case, only three, right? What you do, they are pre-filtered, right? Using the low pass filters, right? To band limit the same. You take them and you try to perform the band limiting operation of that, because ultimately you are going to do the sampling. So there will be a fixed sampling frequency. So you will make sure that the frequency content of each of the signal uh, is band limited, right? Frequency should be you select it in such a way that highest frequency is lesser, twice the highest frequency should be, right? Or you use a sampling frequency more than the twice of this band limited value. Okay, so you remove the high frequency component that are not needed. All right. Okay, this low pass filter outputs are actually, you are going to, right, perform what is called as a sampling that is using the PAM modulation technique. Before that, what you do, you use a commutator, right? The rotating sampling switch known as a commutator extracts one sample from each of the output. All right. Okay, before that, let me write the sentence which I mentioned just now. That is, the LPF outputs are sampled. How do you sample? Sequentially. Okay. And you use a commutator. I have to talk about a commutator now. So there is a rotating and sampling switch. Okay. It's called as a commutator. What is the job? It extracts one sample from each input message signal per revolution, right? In the sense, refer back to this diagram. Whenever the sampler, that is this arrow mark, this rotates, right? One revolution means one sample of each of the message signal. That's what is the meaning. Okay, that's pretty much straightforward. So the output waveform of the commutator will be then converted into the PAM waveform that contains individual message samples periodically. We are trying to perform what is called as a interleaving, right? Each message is from every message signal, we are collecting one sampling, one samples, right? And we are interleaving them, right? And then we are converting into the PAM. Okay, so I can write it in this way. So the output of the commutator, output of the commutator is converted to PAM waveform. How it is made up? So that contains the individual message samples periodically. All right, there is a interleaving, so I'll write interleaved in time. Okay, so it is PAM signal. So I know that PAM uses infinite bandwidth. Since there are multiple messages contained in this particular PAM, no problem, we can transmit that. All right, so anyway, we can which gets transmitted until even in time, comma, which can be transmitted over a communication channel. You try to send it over a given channel. Okay, all right. Now, so let's look at the frequency domain view. So whenever this is sent, it will be passed over to the channel. So till there it is done. Now we'll look at the what are the characteristics or how fast the commutator should sample, etc. We need to see that, right? So let's look at the frequency domain view. Okay, so let us make an assumption here, that is, let all of the message signals, each of the message signal have the bandwidth equal to W hertz. So bandwidth is fixed, right? So this implies commutator should rotate at a rate greater than 2W, correct? This means commutator rotation speed must be, okay, I can give a notation here. So that itself is a sampling, where the sampling is being done, right? So Fs should be greater than or equal to twice of this W, so that the successive samples from a given message signal are spaced by the required amount in time. So the commutator rotation speed Fs should be greater than 2W. I'll continue here, so that what is our actual requirement? The one which I'm going to write now is the actual requirement. Okay, so that the successive samples from any given message I'll write message signal so that it becomes very clear. Any signal, successive samples of a message signal are spaced, right, in time with what is the sampling duration Ts. So this is decided. Ts is equal to 1 by Fs. So Fs is already decided. So this means Fs, this value should be lesser than or equal to 1 by 2W. Right? So you see, it is Fs is greater than means 1 by Fs is lesser. So obviously, right? So that's what I said. So now we have discussed about the timing interval Ts. So the time interval Ts that actually contains one sample of each of the message is called as a frame. So now let's try to look at that. So let me write that sentence first. That is the time Ts containing one sample from each of the message signal, right, has a name. It is called as, it's called as a frame. Now between any two samples of the same signal, right, in the sense I sent S1, before the next sample of S1 comes, there should be n more number of samples. What are the n more samples? N is, in this case, there will be two more samples, because first I send this, then I send second one, then I send third. So after the third is sent, once again the first gets. In the sense, you see, one complete cycle takes three samples. In the right, so between the two samples of G1, I should have other samples also in place, right? Because one complete cycle is that. So let's try to write a frame now. So how the frame should be represented. Okay, so I'll write, let me write, okay, the first one I write. So let me say if I have a signal called the G1 of T, right? I'll try to write the G1 of T with the time. So let me say this is the time axis T, and I'm trying to plot only one signal. Say this is G1 of T. Let me assume that the G1 of T is like this. So how should be the sampling that's happening, right? Something like this. Now this is one time, so I sample here and I hold it. So then after some time, let me assume at the center, maybe I'll have my next sample coming up. This is just an assumption, you don't have to do this exactly. Okay, so there is a second sample happening, and after the same amount of time, maybe I'll have my third sample. This is the sampling of G1 of T only. So what is the sampling duration now? You see, this is, I'll say this is 0. The one which is on the right side should be Ts. This should be minus Ts, because that is the requirement of sampling for a given signal, right? This is a Ts. Okay, but now let us see what happens when I do the this is what, if there is no commutator and I'm sampling only one signal, this should be Ts. Now what happens is, between the G1 of T, there should be G2, there should be G3, then there should be G1 once again, correct? So that's what is happening whenever I try to perform the PAM representation for all the signals simultaneously. Okay, so that's what is important now, right? This was just G1 of T, but what I do now, I'll replicate this once, and I'll write all of them together. Okay, so this is how it's going to look like. Let me paste. And now you see it's not just g1 of t. So what I do, I'll just erase this. I don't know. And you see it's not just g1, so I have to eliminate this. There is no the black line should not be there because that corresponds to only g1 of t as of now. So we know that it is not only g1 of t, it has all the other signals as well, right? G2, G3 as well. So because of which I cannot simply write one waveform. I can retain the, I just have to retain this. Now you see, right? I'll assume that there is another completely different signal that is G2. So I'll try to write the signals corresponding to G2 like maybe a different color. Oh, sorry. Okay, so this is a sample corresponding to G2. The duration remains same. Okay. This is a G2, right? I have its next sample coming up, maybe over somewhere here. Okay, and I'll use a different color now to represent the third signal, that is G3. So maybe G3 like this. This is a sample corresponding to G3. Okay, corresponding to the same G3, I have its next sample coming up. Maybe that has a different amplitude, possible, like this. Okay, so the important point is that the width of each of the pulse is same, that is capital T. Okay, so I'll write at two different locations. So one here. So this width is capital T. Now you see the same width is maintained everywhere. So this width is also capital T, right? I'll write another for a green one. That's also T. So everywhere it is same. Okay, so I retain G1. Now it's all of them together. Multiplexed PAM waveform is this. So the first one is, okay, I'll give a naming so that when you read, you understand. Okay, so this is the PAM of G1 of T. That's what you can see here. But now we do the multiplexing. So this is the multiplexed PAM. It looks like this. So, right, if you want, we can try to do one more thing that makes it very clear. So I'll use the colors. Okay, so the red colored waveforms are something like, so this is what is this? This is G1 of T. Okay, I'll use another color for G2. So you see, let's assume this is how the G2 looks like. Okay, so this is what is G2 of T. And there is a G3. Okay, so that is G3 of T. So it is multiplexed. Right now, right, you see there is another concept. Now I know that between two red pulse or two blue pulses or two green pulses, I have a same duration that is equal to TS. All right, let me mark it. So between any two. Okay, so let me mark between the two blue, two greens, that is equal to TS. But now you see the difference. So the difference comes into picture whenever I try to mark between Okay, between any other two. Okay, so okay, let me show you. So that is between this and this, between this and between this and this is also all are same. Okay, that is, in this case, it is how much? The whatever TS we had, it's divided by 3, correct? Because in one TS I have 3 different samples coming, correct? But you see now, in general, this gap is right. So I can write whatever TS, it's divided by N. So where the capital N is the number of samples or number of message signals. Okay, so this is also TS by N. This is also TS by N. So here you see the capital N represents the number of message signals. Okay, now I'll mark a frame, right? Because we discussed about the word frame here, right? So starting from 0 to TS, or whenever okay, this is also fine. Already we have marked. I'll just write a frame. Okay, so whatever is this distance, right? Here to here, you see all the samples of each message signal is there in this. Okay, so that's why you call it as it's a frame. Complete TS duration, whatever you send is called as a frame. Within the TS, whatever you send will be called as a frame. Okay, so that finishes the whole concept. Now, what is the minimum bandwidth required? We just have to calculate that. That's the last point we write here. The minimum bandwidth of a PAM based TDM waveform, that is B is equal to summation I varying from 1 to capital N. This is Wi. So here we have Wi is the bandwidth of ith message signal. So I write that is BW of ith message signal. Okay, so each bandwidth should be added together to get the total bandwidth. Okay, that's the only point here, right? If you have, right, in the previous case, you see in this above diagram also, here we assumed equal bandwidth for each of them, right? So there was W for each message. So, right, that was the concept we used in this discussion. But now you see, in general, if you are talking, right, there should be, this is the equation that we are going to use to calculate the total bandwidth of a PAM TDM system, right, in general.